So let's continue our discussion and let's look at Charles's law, part 2. So Charles's law essentially is this idea that the volume of a gas is proportional to the temperature. So in this experiment, we took a syringe and we recorded the volume at 3 different temperatures. So at room temperature, what was the temperature at room temperature? What was our first reading? What was our room temperature? Looking through our data, I'm gonna need your help on this one. So 23.7 degrees Celsius, okay. And what was the volume? What was the volume roughly? 4.2 milliliters. Okay, then we immersed our syringe in ice water. What was the temperature of ice water in this case? Oh, the volume was 3. What was the temperature or the volume? What was the temperature of ice water? 3.2 degrees Celsius, okay. And what was the volume? 3.8 milliliters, okay. Next, we placed our sample in hot tap water. And what was the temperature of our hot tap water? What was the temperature of our hot tap water? (55.8 degrees Celsius). And what was the volume? 4.5 milliliters, okay. Perfect. So now what we're going to do is we're going to take our volume and we're going to convert our volume to liters. Okay. So we have 4.2 milliliters times 10 to the negative third liter per mil. So we have 0.0042 liters, 0.0038 liters, and 0.0045 liters. So this is our volume. Now let's do the same thing and let's convert our temperature to kelvins. So we have 23.7 plus 273.15. Gives us 296.85. 3.2 plus 273.15 gives us 276.35 Kelvin. Okay, now we have 0.004, whoops, we have 55.8 plus 273.15. That gives us 328.95 kelvins. Okay, so now we have volume and temperature. We are going to plot this data in Excel to try to find a linear relationship between volume and temperature. So that's our goal. So we're going to begin to open Excel. So allow me to share my Excel sheet. Okay, so now we're going to make a plot of, oh, whoops, sorry about that. We're going to make a plot of temperature in Kelvin versus volume in liters, okay?
Is it possible for us to use like, well, I don't know about anyone else, but like I don't think I can go on Excel on my laptop, but
Google Sheets will work just fine.
okay, cool.
Yeah, I'm just doing it in Excel because it's the most easily exportable file format that I can post on Canvas. Just because for Google Sheets, it sometimes doesn't quite behave as well as I would like for some of these graphing components.
Yeah, okay, cool.
So let's now input our data. So our volume, 0.0042 liters. Okay. Our temperature, 296.85. Okay.
Wait,
27.
Professor, so you want the temperature in Kelvin and the volume in liters, even though in
Yeah.
the directions it says milliliters in Celsius?
Yeah. I already converted it to Kelvin and liters, and it'll be much easier to see this time.
Okay.
Just because Kelvin is known as absolute zero, so it's always better to have your temperature in kelvins and your volume in liters when you're dealing with gases, as it makes it easier to see some trends associated with gas behavior. And we have those already converted, so all you have to do is just enter them into our Excel sheet. And I'm just gonna move the ordering around just so that way it's in ascending order. So we have temperature versus volume, and just like before, we're gonna generate a graph. So what we're gonna do is we're gonna select both of our cells, we're gonna hit insert, and insert a scatter plot. So if everything is done correctly, when you add your axis titles, you'll see on the y-axis, you have your volume in liters, and on the x-axis, you have your temperature in Kelvin. Volume versus temperature, Kelvin for a air sample. Okay, so now that we have our data points in place, what we're going to do is we're going to right click on our data and we're going to add a trend line. Now, in the trend line settings, you're going to want to display the equation in the chart and display the R squared valued in the chart. Okay. And now what you're going to do on the trend line is we're going to forecast our trend line backwards 280 units. So you're going to enter 280 periods into the forecast backwards.
Can you explain how you did that again, please?
Yep. So let's pretend we're going straight from scratch. You're going to select our data. We go to insert. We click on the scatter and we insert our scatter. Then, whoops, let me hit undo really quickly. Then we hit add. We add our axis titles. So we have our volume on the y-axis and our temperature in kelvins on the x-axis. We'll write our title as volume versus temperature, Kelvin, for an air sample. And now what we're going to do is we're going to right click on our data you'll see in the drop-down menu, there's an Add Trend Line button. We'll click on that, Add Trend Line, and then there are multiple little drop-downs. You'll hit Display Equation, Display R Squared, and then you'll hit in the forecast area, you'll enter backwards 280 units. Does that make sense?
Yeah, thank you.
Perfect. So now what we're going to do, we're extrapolating our line until it intersects the x-axis. Okay, so looking at our plot, we have not quite intercept our x-axis. So what we're going to do is we're going to continue to forecast backwards an additional to about 300 units. So here's our forecasted trend line, and here's our actual trend line. And so these are the two graphs that I'd want to see for this experiment. Now, what can we do with this information? Well, what we're going to do is we're going to figure out the temperature that our line intercepts the x-axis. Note that condensing something down to 0 volume doesn't actually make any physical sense, and this Charles law falls apart very quickly at very low temperatures because you start to condense your gas. I mean, by definition, particles must have an inherent volume. They do take up an inherent amount of space. So even at low temperatures, the volume can never be 0, right? Atoms have mass, they take up space. And what this is helping to show is that to get to low volumes, it's impossible. And in order to even approach low gas volumes, it requires very, very low temperatures. We've never seen absolute 0. So it's not particularly plausible to say, well, if we just cool a gas down to this temperature, its volume will go to 0. No, the gas has an inherent baseline volume. So this is start helping to show, looking at Charles' law, how can we use it for predictive power? What ranges does it work? So in most temperature ranges, Charles' law works pretty well for ideal-like gases. Even then, our fit is not perfect, even under this small temperature range, but it's pretty good. However, at low temperatures, things begin to fall apart. So, was everyone able to generate a plot? And is everyone able to extrapolate their plot? We're now going to show one other calculation. So looking at the equation here, your value of absolute 0, is going to be your x-intercept. So what you're going to do is you're going to calculate the x-intercept, which is the value of x when y is equal to 0. So to do that, we're going to take our value b, which is our y-intercept. So we're going to take 0.0003, multiply it by -1, and divide by 1 times 10 to the -5th. which is our slope. And we get a value for absolute zero of -30 Kelvin. Again, just to show that one more time, the absolute zero, so the value of absolute zero obtained from extrapolation is going to be equal to your y-intercept times -1 over your slope, which we got -30 Kelvin. So if we wanted to do a quick percent error calculation, we take our -30 minus 0. Let's write this -30 in terms of Celsius. So now we're going to take 243 minus -243. Well, if we're converting from Kelvin to Celsius, we'd subtract. So we have -303. This is our experimental absolute zero. Our theoretical value is -273.15. So then our percent error is going to be equal to our experimental minus our theoretical over our theoretical. Times 100%. So this gives us a percent error of about about 10.9% or about 11%. So is everyone comfortable with generating their plots and extrapolating their plots? Does this idea make sense to everyone? The point at which your volume is 0, so the point at which your line intercepts the x-axis, that is the temperature of absolute 0. We then write the temperature of absolute 0 in Celsius, and we use that to calculate the percent error. The reason why we do that is if you keep it in kelvins, you run into an issue where you try to divide by 0. Does this make sense to everyone? Any questions on analyzing the data from part 2 of this experiment? Otherwise, you have all the information you need to complete your laboratory report and turn in your graphs for part 2 of the Charles' Law experiment.